Hello, and welcome to a digital statistics lecture for Salt Lake Community College. In this video, we're going to be going through section 5.4 in Math 1040, Conditional Probability and the General Multiplication Rule. We're going to be continuing where we left off in 5.3, where we talked about how to deal with the multiplication rule, and what we're going to be dealing with is how to deal with situations where you have dependent events. In order to talk about dependent events, we're going to be discussing conditional probability. You may remember conditional probability, or at least conditional distributions, from section 4.4, where we talked about how to set up relative frequencies, or really probabilities, depending on some given condition. We're going to be using that more in depth here. A conditional probability is the probability that an event F occurs, given that an event E has occurred. That word given is very important, and what the given probability is also very important. It says given that the event E has occurred. That E is going to be the one that helps influence the overall probability of the event F. We have that written as the probability of F given E. That vertical line there we even read as the word given. That does not mean division. It is not a division sign. It means the word given. So it all depends on what E is. If E has already happened, we're going to be asking what the probability of F is if E has already occurred, which may influence the probability of F, it may not. It all depends. Generally, if we're doing the conditional probability rule, it's going to be an overall fraction, and the main important point is to focus on the given part. You'll notice that I keep harkening on that because the given part is the most important thing in conditional probability. The probability of F given E is the probability of E and F over the probability of E. That denominator is very important. Whatever the given probability is going to directly influence whatever the denominator is. You can also do these instead of having probabilities over probabilities, you can simply do counts. So you can, instead of having the probability of E on the bottom, you can simply have the amount of E on the bottom, or how many of the outcomes are in the event E, which is generally how we're going to do most things. We don't really need to do two probabilities over one another, which gets more complicated than it needs to be. But the most important point is to focus on what the given event is, because that will influence how the denominator is going to be set up. You'll notice in all the questions moving forward here, I am going to be focusing on the given part first and setting up the fractions in terms of that first. It's the most important point. Talking about the conditional probability will allow us to deal with also the general multiplication rule. If you remember, we had the multiplication rule before for independent events. There we go. We had the general multiplication rule before for independent events. We had the probability of E and F as the probability of E times the probability of F. We simply multiply those together. However, now, if we're doing the probability of E and F, what we're going to do is the probability of E first, which is the same as it was before. We're still starting with whatever the first probability is. And then we're going to be multiplying by the probability of F, but now it's going to be the probability of F given E. So given that E has already occurred, now what is the probability of F? We also call this the general multiplication rule because this still applies for independent events. If you have independent events, the given portion will not matter, and the conditional probability will not be altered. For example, when flipping coins, it does not matter what happened on my first flip. The second flip still has the same probability it originally had, so there's no change there. But when I'm drawing cards without replacement, and I draw a card and I set it aside, now the probability of me drawing whatever card next is going to be changed because there's less cards available to be chosen. So that is what we're going to need to consider. How does the probability get influenced depending on what the previous events already were? I have this starred note here as a rule of thumb. If the sample size is less than 5% of the population, we treat the event as independent or close enough. Realistically, whenever we gather any sample from a population, it cannot be independent because the probability, say if I have 1,000 people, the probability that one person gets selected is 1 out of 1,000. Wrong cursor. The probability that somebody gets selected is 1 out of 1,000. Well then, once that has happened, the probability the next person gets selected is 1 out of 999 because that person that was previously selected is no longer available. Therefore, the probability has changed. However, that's a really hard point to get caught up on, and it makes a lot of statistics more complicated than it really should be. Therefore, we have a general rule that if our sample size is small enough compared to the population, specifically if it's less than 5%, then we're going to consider the sample to be independently selected. Because the change from 1 out of 1,000 to 1 out of 99 is so minuscule that it doesn't really matter. If I even try that in my calculator, 1 out of 1,000, sorry, 1 out of 1,000, there we go, 0.001, and if I do 1 out of 999, I get 0.001 again, just with a very, very small change. It takes, what was that, 5, 6 decimal places for the decimal to be different. So it's such a small, minuscule change that it doesn't really influence the overall system terribly much. I star this because it's not as important now, but it will be important for the rest of the class. We will keep using this as a general condition in order to, as we'll talk about later, claim that something is bell-shaped. So it is going to be very important starting in chapters 7, 8, 9, 10, and 11. You will see this note show up a lot. Another important note is that two events E and F are considered independent if the probability of E given F is the same thing as the probability of E. What that means is that if they're independent, then that means the given condition there does not matter at all, and it doesn't change the overall probability. Likewise, if they're independent, you could also consider the other way around. The probability of F given E should be the same as the probability of F, still implying that that given condition I have is not important to the overall system. This is going to be a nice note because this will allow us to check probabilities that we've calculated and be able to say with mathematical reasoning why something is independent or dependent without just trying to base something on subjective reasoning. So we're going to be able to look at the data that we've calculated and say for sure that something is independent or dependent or based on the data that we've calculated, which is going to be a nice confirmation, really. We'll come back to this in a couple examples. The rest of this section is going to be just a bunch of examples from page 11, I think, up to page 15. We have about 4.5 pages or so of examples because these can be a little bit tricky. And this is really where the peak of chapter 5, I say, is in terms of difficulty. At this point, it'll start to depreciate after 5.4. So if you've had a good time moving forward up to this point and you're okay after 5.4, I'll say that you definitely got over the hump of the course. Okay, so let's go through some. A box contains 6 blue marbles, 5 red marbles, and 2 green marbles. So 6 plus 5 plus 2, that's 13 marbles overall. If 2 marbles are randomly selected from the box without replacement, that means that they are not put back. What is the probability that both are blue? So we had this in 5.3, the probability of both blue. Both is a key word that helps us identify this is going to be a multiplication, because what this means is the probability that the first marble I select is blue and the second marble I select is blue. That's what both means. Therefore, this is going to be the probability that the first marble is blue times the probability that the second marble is blue, and from now on we're going to use the general multiplication rule, which says the probability the second marble is blue given that the first one was. So that means the first probability, we have 6 blue marbles out of 13, so simply 6 out of 13. That's pretty straightforward. But now we already selected a blue marble out of that bag. What that means then that the second blue marble doesn't have as high of a chance. Since there are no longer 6 blue marbles in that bag, there are only 5 blue marbles left over. 6 minus 1 equals 5. Similarly, there's overall no longer 13 marbles in the bag anymore. One has already been taken out, so there's only 12 remaining. That would be an instance of conditional probability. This is where dependent events come into play. The probability of the second marble being blue did depend on whatever the first one was. So the probabilities do get altered. If we multiply these, 6 times 5 will give us 30. And 13 times 12 will give us 156. So 30 out of 156. Let's do another one. Probability the first is blue and the second is green. Whoop, sorry. So we'll write that down as the probability of B1. The first one is blue and green for the second one. Again, notice that they use the word and there to connect these statements. So that means we're going to multiply again. This is going to be the probability that the first one is blue times the probability that the second one is green, given that the first marble I selected was blue. So the probability of the first marble being blue, we had that before. That was 6 out of 13. And the probability that the second marble is green, well, overall there are 2 green marbles, and what I selected first was a blue marble, so there are still 2 green marbles in the bag. However, even though there are still 2 green marbles in the bag, there are only 12 marbles overall. We multiply these together. 6 times 2 will give me 12. 13 times 12 gives me another 156, just like the previous problem. You can also change these in decimals if you want to. I like them as fractions, though, because it allows us to easily compare them. Lastly, the probability that the first one is green and the second one is blue. I recommend actually at this point to pause the video, see if you can find this one on your own, and see if you find something interesting about this problem. Okay. So this is going to be the probability that the first marble is green times the probability that the second marble is blue, given that the first marble I selected was green. Well, the probability of the first marble being green is 2 out of 13. There are 2 green marbles out of the total 13. Then when I've already selected a green marble, there's only 12 marbles left overall. And there were originally 6 blue marbles, and there still is 6 blue marbles, because what I already selected was 1 green marble. So that means the probability is 6 out of 12. If you did this on your own, you may notice that if you multiply these, you get 2 times 6 is 12 out of 156. What you may see now is that this is the exact same answer we got from Part B, which had a very similar question. Part B asked the first marble is blue and the second is green, whereas Part C asked the first is green and the second is blue. Some may say, well, of course, they're the exact same situation, and generally, yes, they follow under the same event. The event that they both fall under is 1 green, 1 blue. However, 1 green, 1 blue can happen in 2 ways. You can either have the first marble being blue and the second marble being green. Wow. The first marble being blue, wrote G in blue. The first marble being blue and the second marble being green. Or you could have the first marble being green and the second marble being blue. That's how we could have the event of 1 blue and 1 green. Since it can happen in 2 different ways, those are 2 different outcomes that fall under the same event. So if I wanted to find the probability of 1 blue, 1 green, I would need to find both of these and add them together. The fact that they end up being the same probability is going to be a very important point moving into Chapter 6. So keep this in mind moving forward. Okay. On the next question, we have a multiple choice quiz with 4 possible choices for each question. So let's say A, B, C, D. Each question has A, B, C, D, and there's 4 questions. The student answers all 4 questions by making random guesses. Therefore, we'd say the probability of a correct answer, I'll say E, I guess, just to say probability of the event. Probability of the event of getting a correct answer should be 0.25. The reason it's 0.25 is because on each question, there's a 1 out of 4 chance that you get the correct answer, whether that correct answer is A, B, C, or D. So that's the probability of getting a question right. A asks us, find the probability that all 4 answers are correct. Well, all 4, we had a few of these in the last section. All 4 is another repetition situation. And all 4 means that you get the first question right. So a probability of E1 and E2. And you get the third question right. And you get the fourth question right. Now to evaluate this, we notice that the questions are independent of one another. Whether you get a question right for the first one is not going to influence how you get the next few right because you are making complete random guesses. You are not changing your answers or saying that you cannot use the same letter for different questions. You are simply making random guesses. So they should be independent. Therefore, the probability that you get the second question right, given you got the first one, should not change. Same thing for the third and the fourth. So we have the probability of you getting the first question right is 0.25, which is also true for the second, third, and fourth. So we can simply solve this by taking it to the fourth power, because we would be multiplying by itself 4 times. If we do 0.25 to the fourth power using the caret above the division sign, we get 0.0039. So not a very high chance. Less than 1% chance you get all 4 questions right by making random guesses. Second, we have find the probability that all 4 answers are wrong. Well, we know the probability of E, which is getting a question right, is 0.25. Therefore, we know the complement of it as well. The probability of getting a question wrong should be 0.75, or 1 minus 0.25. Therefore, the probability of all 4 being wrong is going to work just like the previous one. We're going to multiply, in this case, the complement by itself 4 times. So this will give us 0.75, which is the probability of getting the first question wrong, to the 4th power. If we do that, we get 0.75 to the 4th power, which gives us 0.3164. So a much higher chance of getting them all wrong than getting them all right. C asks the probability that at least one answer is correct. At least one is a very particular phrase. At least one means that you either get the first question right and the rest wrong, or the second question right and the other one's wrong, or the third question right and the other's wrong, or the last 2 right and the other's wrong. There's a lot of ways we can do this. However, we talked about in 5.3 that you can solve this in an easier way using a complement, specifically doing the complement of 1 minus the probability of none being correct. So since we were looking at the probability of at least one being correct, we can do 1 minus the probability of none being correct. Well, none of them being correct is the same thing as the probability of all 4 being wrong, which is what we just did. So that's 1 minus 0.3164, which will give us 0.6836. Yeah. Just do that for confirmation. 1 minus 0.3164, 0.6836. Okay, one more. Probability that 1 is wrong and 3 are correct. This is what I was also talking about, or this is going to be similar to what I was talking about before with the blue and green marbles. 1 being wrong and 3 being correct, order not being specified, can happen in a lot of different ways. Let's write this down. You could have the first being wrong and the other 3 being correct. You could also have the second being wrong and the other 3 being correct. Or the third wrong and the other 3 correct, or the last one wrong and the other 3 correct. Those are the 4 situations that we could have of getting 1 question wrong and 3 questions correct. However, we noticed before when doing the probability of blue and green that these situations should end up being the same regardless. And we can show that here. If you getting the first wrong and the other 3 correct, notice that I even used the word and there, means we're going to be multiplying. So the first one being wrong should be 0.75, and the second one being correct is 0.25. And the third one being correct is 0.25, and the fourth one being correct is 0.25. Or 0.75 times 0.25 to the third power. Now, if I did that for the second one, I would have 0.25 for the correct answer, times 0.75 for the second one being incorrect, times 0.25 for the third being correct, and 0.25 for the fourth being correct. That's going to be the same thing. With multiplication, we have the associative and commutative properties that allow us to multiply in any order. This is the same thing as 0.75 times 0.25 to the third power. It'll be the exact same answer. And you can assume the same thing for this. All 4 of these are going to have the exact same answers. So this one and this one. Well, some may say, well, why do I need to care about then? Why don't I just do one of them, because it's going to be the same for all of them, and just call it a day? Why don't I just do, in my calculator here, why don't I just do 0.75 times 0.25 to the third power? Because that's what all of them come out to be. Is that not the correct answer? The reason that is not necessarily the correct answer, because that's only one way it can happen. Since we're considering the event of 1 being wrong and 3 being correct, that means we need to consider all possible outcomes where that could happen. We just calculated a single outcome, so we do need to calculate the other 3. But since they all can happen in the same way, we can do this in a little bit more of a shorthand way. We can instead say, oh well, there's 4 different outcomes that all have the same probability, so let's just do, instead of adding them up, we can simply do 4 times that probability, the 0.75 times 0.25 to the third power, because they're all going to happen in the same way. So if I were to add them up and they all have the same value, that's the same as multiplying by 4. Therefore, I can find this answer by taking the number I have in my calculator there and multiplying that by 4. What we get is 0.046, and we've done 4 decimal places, so 0.0469. And that would be my final answer. So if there are multiple outcomes that fall under the same event and we only calculated 1, we do need to calculate the rest. But in a lot of these cases, they end up having the same probabilities, which is more convenient. So we just need to find 1 and multiply by how many ways it can happen. Again, you'll see more of this later on in Chapter 5 and 6. Okay, I think we have 2 more pages here. 3, actually. Okay. Suppose you just purchased a new CD that has 13 tracks. After listening to all the songs, you decide that you like 5 of them. That means, alternatively, you dislike 8. So we'll say the probability that you like a song, I'll do L, I guess. The probability that you like a song is 5 out of 13. And the probability that you don't like a song, so the complement of that, would be 8 out of 13. Okay. With the random feature on your player, each of the 13 songs is played once in random order. Find the probability that among the first 2 songs played, you like both of them. Would this be unusual? Okay, well again, we see the word both. That's going to be a multiplication rule, because that means the first one you like and the second one you like. The probability that you like the first one and you like the second one. Well, that'll be the probability that you like the first one, and we'll use a general rule and see if it matters, times the probability of liking the second one, given that you like the first. Well, the probability you like the first song we wrote above was 5 out of 13. But then the probability that I like the second song, given I like the first, now there's only 12 songs remaining, because I already played one song on the CD. Furthermore, I played one song that I like, so there's only 4 songs remaining that I like. Therefore, we multiply these. 5 times 4 is 20. 13 times 12, we did before a couple pages back, is 156. And that is our final answer. How about B? You like neither of them. All right. Well, you like neither of them means that the probability that you dislike the first song, which is the complement of liking it, and you dislike the second song. So the probability that you dislike the first song times the probability that you dislike the second song, given that the first song that you played you also dislike. Well, the probability that you dislike the first song we wrote above was 8 out of 13. And now that one song has been played, there's only 12 remaining. Of those 12, one song that I dislike has already been played, so there's only 7 songs that I dislike remaining. The other 5 I do still enjoy. 8 times 7 will give me 56 out of 156. So far, so good. And that's the only way that either of those can happen. You like the first and the second, you dislike the first and you dislike the second. It's the only way those two can happen. C says you like exactly one of them. Well, that could happen where you dislike the first and or you like the first and you dislike the second, or you dislike the first one and you like the second. Since that can happen in 2 different ways, what we're going to do is solve for one of them and multiply by 2, because we've shown before that the probabilities will still be the same. So let's do the first one. Probability that you like the first song times the probability that you dislike the second song, given that you like the first one. Well, that will give me the probability that I like the first song is 5 out of 13. Since one song has been played, there's only 12 songs remaining. Of those songs, the amount of songs that I dislike is still 8. The first song that I played was one that I like, not one I dislike. So there's still 8 songs that I dislike in that CD. That's what I would need to do to solve for one of these. And then since the other one would be the exact same thing, we can simply take this and multiply it by 2. So we get 2 times this. If you want to keep this as a fraction, when you multiply by a whole number like 2, you can consider that as 2 over 1. So we get 5 times 8 is 40, times 2 is 80. Out of 13 times 12 is 156. As a funny note for that one, actually, if we consider the sample space of all possible things that can happen when you play 2 songs, you could either like both of them, you could dislike both of them, or like one of them. Those are the 4 things that could happen. Well, we already solved for liking both and disliking both. Therefore, if I want to solve for liking one of them, I could also do that using a complement. I could do 1 minus these 2 probabilities, which we solved was 20 out of 156 and 56 out of 156. I could take those away from 1, or 156 out of 156. And what I would get is 80 out of 156, which would be the solution that we just solved for. So that's another way that you could have solved that problem using complements. Some people see things different ways, so it depends on how you want to go about it. Sometimes the direct way works, sometimes the indirect way can help a lot as well. Now the last part, D, or sometimes E depending on your notes, says repeat parts A through C if a song can be replayed before all 13 songs are played. Now I won't do all of them, but I will just discuss what would happen. If a song can be replayed before all 13 songs are played, what that would change would be the given parts of each of these probabilities. If a song can be replayed, then that means it does not matter what song was played the first time because that song is now back in the queue and could be selected yet again. Therefore, the condition no longer matters anymore because now the probability of you liking a song or disliking a song is independent of what had already happened. Therefore, these probabilities that change to be something out of 12 would no longer do that. This one would still be 5 out of 13. This one would still be 8 out of 13. And this one would still be 8 out of 13. So the probabilities would not get altered anymore because something had already happened. That's all that would occur for D, and you would get different probabilities. You get values at 169 instead. But I'll let you do that on your own if you so please. Let's work with this one, a two-way table. So harkening back to chapter 4.4. A group of students were asked if they carry a credit card. The responses are listed below. So we have credit card carrier, not credit card carrier, and we have them split up into two groups, freshman and sophomore. So our two qualitative variables are level of education, or I guess graduate level, freshman or sophomore, versus do they own a credit card. So two qualitative variables. First, before we continue, what we want to do is solve for the totals, or if you recall, this is called a marginal distribution. We'll just keep it as a frequency marginal distribution so we know what the totals are. So 23 plus 15 will give us 38. 37 plus 25, that will give us 62. And 38 and 62 total to 100. If I total the rows, 23 and 37 add up to 60. And 15 and 25 add up to 40, which also totals to 100. So everything checks off. A, if a student is selected at random, find the probability that a student is a sophomore. Okay, so we're simply just saying what's the likelihood that if I choose somebody that they are a sophomore. So we'll say probability of a sophomore. In this case, that's 40 sophomores out of the total amount of students that could be selected, which is 100. Nice and easy. B says if a student is selected at random, find the probability the student is not a credit card carrier given that the student is a sophomore. That given word is the most important. That means that we're doing a conditional probability. We're doing the probability that the student is not a credit card carrier given that they are a sophomore. Now, if you remember at the beginning of this section, I talked about that with given probability, the most important thing you need to focus on is the given situation. The given event will determine what your denominator is going to be. My denominator here, since the given part is sophomores, my denominator is therefore going to be all sophomores. So what we're considering here is not all of these values in this list anymore. We're only considering this row. We're considering only sophomores. Any freshmen are no longer part of the consideration. So we're not talking about all 100 students anymore. We're only talking about the 40 sophomores. Of those 40 sophomores, 25 of them are not credit card carriers. Let's also change these just into simple decimals just so we have them. 40 out of 100 is 0.40. And if you do 25 out of 100, that should give you 0.625. But let's check that. 25 out of 40. Yep, okay. All right, so that's how given probability is going to work. Now the next one says that the student selected at random, find the probability the student is a sophomore given that he or she is not a credit card carrier. Some would look at that problem and say, well, that's the same thing as last time, isn't it? No, it is not. In this case, the given event has changed. I'm no longer considering all sophomores, I'm considering all non-credit card carriers, which looking at my table is this column. I'm only considering those individuals in that column. Therefore, my total amount of people I'm dealing with is 62. Overall, of those 62 individuals, 25 of them are sophomores. Notice that every time I'm framing it in terms of what the given event is first. That's the most important point. 25 out of 62 gives me 0.403. Lastly, are sophomore and not a credit card carrier independent? Now that's kind of an odd question. In this case, we don't need to answer this with subjective facts. We don't need to look at this and say, well, I believe that they are independent because of so and so. I should be able to solve this now using data. We talked about before that you can consider events to be independent if the given condition did not change the probability. So, from the first page we had that if you have the probability of sophomore, for example, that should be the same thing as the probability of sophomore given not a credit card carrier. Or, if you have the probability of not a credit card carrier, that should be the same thing as the probability of not a credit card carrier given that they're a sophomore. Essentially, it means that the given condition did not influence the overall probability in any way. Well, thankfully, we already solved a couple of these. We know the probability of a sophomore from the first question to be 0.40, and we solved the probability of sophomore given not a credit card carrier in this question, part C, 0.403. Therefore, we have that these two probabilities are roughly the same. It hardly changed at all. We don't want to be too strict and say that it changed ever so slightly, therefore they are dependent. We want to see if the probability changed significantly, which in this case it did not. So, because the probabilities did not get changed, that means that one event did not significantly influence the other one. Therefore, yes, these are independent. Now, we could do this in another way as well. We could consider the other side that I had written over there, the probability of not a credit card carrier equal to the probability of not a credit card carrier given a sophomore. Unfortunately, we haven't solved for that one really yet, but we can. We solved for not a credit card carrier given a sophomore. We found that to be 0.625. And we can also solve for what it is to be not a credit card carrier. Well, not a credit card carrier, looking at my table above, we have that overall there are 62 non-credit card carriers out of 100. So if this is 62 out of 100, 62 divided by 100 gives me 0.62. Still, these probabilities are roughly the same. I'll even change these equal signs to even reflect that, to say that they are approximately equal to each other. They are very, very close. Since the probability has not been changed by much, we do say that they are independent. Now, the level of what the probability needs to change by to say that they are dependent is kind of subjective. I know a lot of people tend to look at the 5% thing again, where if it changed by more than 5%, then they are dependent of one another. But it's a little bit more of a judgment call. I'd say if it just changed very slightly, they are independent. If it changed by more than 5%, I'd say that they are dependent on each other. Okay. One last question, and then we are done. In a recent survey, adult Americans were asked whether they use social media regularly. The following table is based on the results of the survey. So this table is already finished. We have the marginal distributions, which is good. First question is, what is the probability that a randomly selected adult American uses social media given the individual is 18 to 34 years of age? So, probability that they use given that they are in the 18 to 34 age group. Okay, notice that given probability. Since it says given this amount, this 18 to 34 is going to define what my denominator is going to be. In this case, the individuals that are in the 18 to 34 age group, there are 150 of them. I'm not going to be considering all 530 individuals in the sample, only the 150 that follow that condition. Of those 150, the amount that use social media is 117. Next, we have what is the probability that randomly selected adult American is 18 to 34, given that they use social media. In this case, the given condition has changed. It's not going to be the same as before, even though it's using the same two events. Since I'm considering only those that use social media, I am now not considering the 150 individuals, I'm considering the 338 individuals. The 338 individuals that use social media. Of them, 117 are between the age of 18 and 34. Next one. Are 18 to 34-year-olds more likely to use social media than individuals in general, and why? Well, this is asking two different questions. This is asking for what's the probability that they use social media given they're in that age group versus the probability that somebody uses social media in general. Well, we have the probability that somebody uses social media if they're in that age group. We found that in the first part to be 117 out of 150. If we find that as a decimal for comparison purposes, 117 divided by 150, that gives us 0.78. In general, the probability that somebody uses social media would just be the probability that they use social media, no given condition. Overall, there's 338 people out of 530 that use social media, so 338 out of 530. Those fractions are hard to compare, so we can divide that last one, 338 divided by 530. And that gives us 0.64 if I keep to two decimal places. Therefore, looking at our probabilities, we can make a statement about this. We can say, based on the probabilities to the right, we can say that yes, 18 to 34-year-olds are more likely to use social media than individuals in general. That would be our overall conclusion. We see that 18 to 34-year-olds have a 0.78 chance of using social media. We have a 64% chance that somebody uses social media. Okay. I guess we have one last question here. Okay, so we're on the last page. What is the probability that in a room of 12 people, everybody has a different birthday? Well, this is actually kind of an interesting question, and it's a typical anecdote in mathematics. So let's talk about how to solve this. So we have 12 people, and we want to find the probability that everybody has a different birthday. All right, well, in order to do this, we need the first person to have a different birthday than the second, and the third, and the fourth, etc. Therefore, when we start with person number 1, that person could have any birthday in the year. Therefore, they could have any of the 365 days in the year. We're not really considering leap years here. So they could have any of the 365 days available. The second person you have could take any one of those days except one. They cannot have the same birthday as the first person. This would mean that they have different birthdays. If I multiply these together, this would be the probability the first and second person have different birthdays. I can continue this pattern over and over again in order to solve for the rest. So for the third person, I'd have 363 out of 365. and then on and on and on. What I'm eventually going to have is on the bottom, when I multiply everything, I'm going to have 365 to the 12th power, because it'll be multiplied 12 times. And on the top, I'm going to have 365 times 364 down until I have 12 numbers. So let's solve for that. In my calculator, I have 365, so that's the first person, times the second, times the third, times the fourth, fifth, sixth, 7, 8, 9, 10, 11, and 12. Okay, that should be everything. All right, now if we calculate this, it's going to give us a really large number. Yep, it's a large enough number that I can't even write it down. What I'm going to do is simply take that and I'm going to say divide that large number, and just be careful, I'm going to do parentheses, divide by 365 to the power of 12. Whoop. There we go. Divide by that number. Now that number is also going to be very large, but it should counteract the top one, at least to some extent. If I divide those, what I get is a probability of 0.833, or 83.3% chance. So there's an 83.3% chance that in a room of 12 people, everybody has a different birthday. Comparatively, the probability that at least 2 people share a birthday would be the complement of this. What we have is all 12 people have different birthdays. The opposite of that is at least 2 people in that group share a birthday. So we can solve that by doing 1 minus 0.833, and we get 0.167, or 16.7% chance that 2 people share a birthday in a room of 12 people. Now you can extrapolate on that and you can do this situation for more and more people. I think the anecdote is that if you have 30 people, it's very likely that at least 2 will share a birthday. Not necessarily going to happen, but it's incredibly likely. The more and more people you have in a room, the more likely that 2 people will share a birthday. All right, overall, that's it for section 5.4. At this point, you should be able to go through the homework for 5.4 and complete all of that. If you have any questions, feel free to let me know in the comments below or to ask your instructor directly. With that said, I hope you have a nice day.